nice with it.
All right. Okay, so then let's get started. Welcome everybody to the midterm presentation of the A-Lab this semester. And yeah, every presentation is scheduled to for something about 20-ish minutes, 15 to 20 minutes. And that should give us ample of time to ask questions. Also, if you have questions during the talk, you can raise your hand and ask. Of course, don't just shout out. All right. Then let's get started with the first presentation by Harold, Evan, Jonathan, Elias, and Joshua about sonoluminescence.
Yeah, thank you. So again, our group is going over the reproducing sonoluminescence for this year's A-Lab project.
So the general concept behind sonoluminescence is that it is a phenomenon that occurs when a low pressure gas bubble, as seen here, is trapped inside an aqueous solution. It can be trapped in several different ways, but we'll get into that later. And when that bubble is under intense pressure, usually from sound, it will compress rapidly, as you can see, to about the size of a micrometer, and can result in a very brief, low-intensity flash of light. And you can see this video where it's sort of oscillating between like the normal bubble size and getting smaller and producing light. So just a cool thing, the way that sonoluminescence appears in nature, actually, is there is an animal called the pistol shrimp that has a claw, a very big claw right there, that when it violently snaps shut, there's this little groove in the socket that causes a jet of water to shoot out that's very high pressure. And it's a high enough pressure that it can actually overcome the surface tension of the water. And with the bubbles that are created, it's possible for sonoluminescence to appear within those bubbles that are created by the jet. And just a fun fact, when this was first discovered in 2001, it was given the name shrimpoluminescence.
So specifically, we are going to focus on single bubble sonoluminescence. It's too difficult to kind of do multi-bubble. You have to change all the parameters and it gets really complicated. So as you can see here, we're going to have a round bottom flask filled with degassed water, so there's no extra bubbles. We're going to artificially introduce a single bubble using a pipette. And then from there, we are going to put some, it's kind of difficult to see, but we're going to have a transducer on the bottom. It's an ultrasonic piezoelectric transducer. We're going to use that to send high frequency waves into the system. And the reason we're doing that is we want to kind of, as you can see, the bubbles is like suspended in the middle of the water. We want to suspend and kind of trap our bubble. It's kind of the same way where if you have an operator and they sing really high frequencies, it can sometimes, you know, shatter some glass or someone's glasses. In the same way, we don't want to get that far into like breaking the flask, but we want to create a standing wave inside of the flask water system. We're going to try to find the resonant frequency of that, and then based on that frequency, we're going to create a standing wave inside, and it's the antinodes of that standing wave that'll keep that bubble suspended in the middle of the water. So from there, we need to actually like cause the sonoluminescence to happen. So what we're going to do is we're going to use a resonant LC circuit, which we will get into more detail later on, combined with an amplifier, audio amplifier, to increase the amplitude of our frequency waves, and that's going to allow us to get it to the point where our bubble will have a cyclical cycle of cavitating, which leads to collapse, but also it re-expands. It doesn't collapse and just go away, but we want sonoluminescence to be repeated, kind of like in the video that you guys saw earlier. So there are two main theories for why sonoluminescence occurs. They are theories because we don't know the exact reason why it occurs. There used to be a lot more theories about why sonoluminescence happens, but the two main theories, which we will cover, are Brem's radiation and the hotspot theory.
So the first mechanism of sonoluminescence, first theorized mechanism that is EMS radiation, also known as braking radiation. This is the radiation that occurs due to the acceleration of charged particles. This theory suggests that ions that have already been dissolved in the aqueous solution seep out into the cavitation bubble, and as that bubble cavitates, those ions that have entered it accelerate inward very quickly and emit radiation, which we see as a brief flash of light. And what we have here is an example of EMS radiation, which is caused by an electron curving around a nucleus of an atom. Then the next theory is the hotspot theory, which there's a diagram of here, which suggests that as the cavity implodes, the gases already trapped inside the bubble heat up rapidly to approximately 5,000 degrees Kelvin, causing a very hot plasma core to be formed in the center of the bubble, which emits a black body spectrum. And then the final theory is the argon rectification hypothesis, which is a variation of hotspot theory that suggests that all the non-argon noble gases inside the bubble very quickly undergo chemical reactions, turning into soluble products that end up dissolved back into the aqueous solution, leaving only argon gas trapped inside of the bubble. And this hypothesis was proposed to account for the observed phenomenon where the time evolution of luminosity actually decreases for sonoluminescent bubbles that have already undergone a steady state sonoluminescence previously. And then,
so we've talked about what sonoluminescence is and some of the theories behind it, but how are we actually going to reproduce this in the lab with the equipment that we have here in the lab? So the key point is we want to induce intense acoustic pressures, because that's what causes the cavitation to happen, and that cavitation is what causes sonoluminescence. So how can we do that? One way is by using something called, as previously mentioned, an ultrasonic acoustic transducer, and that's just a fancy word for something that converts or transduces or transforms electrical energy into acoustic energy. So it's just like a speaker that's operating at the ultrasonic frequency range. And I'll get into why we need that in a second. But then all we do is we have a flask full of water, and we can attach the transducer to the bottom of this. And then whenever we drive the transducer at some frequency, it will send corresponding pressure waves through the actual flask itself, and that can cause the cavitation to happen. The other key word though is we need pretty intense acoustic pressures for the cavitation to happen. So what we can do is use the resonant frequency of the flask. It's in that system. So typically it's between 25 kilohertz to 27 kilohertz, and that's in the ultrasonic range. That's why we need the ultrasonic transducer. But then we drive the transducer at that same frequency. So let's say it's 27 kilohertz, we drive the transducer at 27 kilohertz also, and that will make the pressure waves, the amplitude of those pressure waves that we're transmitting in there even greater. So that will let us have a better chance of actually cavitating the bubble inside the solution. Or go back over, sorry. Then also we can see on this, our little schematic, we have a second transducer on the side, and we're going to use this one for, instead of driving the flask, we're going to use it as a microphone to pick up the acoustic energy that we're sending from the driver. So then we can see if we're actually at a resonance point. So we mess with the frequency a little bit, and we can see, okay, we're at some amplitude pressure, some amplitude of a signal on the transducer. Then we maybe tune it to the actual resonance, and then we're getting much bigger amplitudes. So we can tell, okay, we're at a resonance point, and we're good to go. And then also, as mentioned earlier, another important part is we need to degas the solution, because you can have, in water, for example, you can have all these gases dissolved in there, and whenever we cavitate or send the pressure waves through the system, even if it's a perfect setup, it will have all these little cavitation sites everywhere. That's really hard to study. So we want to focus on degassing the water, which will let us focus on just doing a single bubble sonoluminescence. The other difficulty is that these transducers actually require like pretty significant voltages to be able to operate them, to drive them. So to fix this, we can take advantage of the fact that we're only really ever sending one like frequency signal through our signal path. And that signal is the resonant frequency of the glass itself. So we'll have some 27 kilohertz signal passing through there. But if we add an LC circuit in series with this, and we create the LC circuit such that its resonance is the same, that same 27 kilohertz, whenever it sees that 27 kilohertz signal, it'll amplify those voltages even greater, which will allow us to actually be able to drive that that transducer without needing like a higher voltage source or something like that. Because maybe the signal generator is like 3 volts, 5 volts peak to peak, maybe 12 something, but maybe that's not enough. But then after that, we're basically good to go, and we just fill our flask with the degassed water. Then we can turn on the electronics and tune that up so that we're at a resonance point. And then, as mentioned earlier, we take a little pipette, a drop of water, we drop it in, and then we can trap that single bubble and cause it to cavitate there. And then we turn off the lights and we can see sonoluminescence happening. And yeah, we can add some coax to get a better signal integrity, but besides that, it's our basic setup.
So the main measurement we want to take is the actual luminosity of the bubble, and it can be measured basically the same way as a star, because it's a radial source, basically a point source if you're far away enough, and you can use the inverse square law and find the intensity at whatever spot we're measuring it from, and we'll use a camera as that sensor, and we'll calibrate it with a light source of known output, so maybe an LED, maybe a laser that has been attenuated to a certain level, so we'll be able to calibrate that camera and actually get like actual numbers out of it. So our main goals are, the 0th goal is to suspend a bubble. That's as far as most groups get, from what we've heard. So hopefully we can do that. If we get there, then we'll try to actually get the sonoluminescence. If we can do that, then we'll measure the luminosity. And if we've done all that and we still have time, then we will just change some stuff and see how the effects on the luminosity, how that works. And some of those things that we would change, the solution temperature, the drive amplitude of the transducer, and the salinity of the water. So using certain salts and things like that. And from what we've seen, in general, the luminosity of the light should increase with lowered temperature and increased salinity. So it might be related just to the viscosity of the water. And that's it. Are there any questions?
All right. Yeah, I would have a question or a couple of questions just about the order of magnitude. So, what is actually, or do you know what the wavelength of the sound waves is in your water flask, or what the speed of sound is?
Yeah. Just from looking up the speed of sound in water, it might be different in our.
Just like an estimate, it does not need to be
As
precise.
a rough estimate, I think it was 1,500 meters per second, and so we get about 5 centimeters wavelength.
Ah, I see. This is really large. Okay. And your bottle has a size of or diameter, or the flask.
Yeah.
As well, what kind of diameter? This is probably in the order of 10 centimeters or something like that.
This guy.
Yeah.
maybe about this, similar to the waveform, right?
Yeah, that could be.
Oh, okay. All right, interesting. And the size of the bubble is typically like millimeters or?
It's on the millimeter scale, but when it cavitates, it shrinks back down to around micrometers.
Yeah, 1 to 50
Mhm.
micrometers is kind of the range.
Okay, and I have one more question about sizes, and this is a pistol shrimp. So, how big is the claw of the pistol shrimp, or I don't know how you call that. But
Do we remember the
so roughly, or how big is the pistol shrimp? Do you know that?
It's probably about like
The
this
size
big,
is-
right?
I think the size is under a foot in length, so.
And I try to. This is maybe a very difficult question for you to answer, but one can maybe think about that at least. Like you say that, or one important ingredient of your experiment seems to be that you have standing waves, right? And I don't really see that the pistol shrimp has standing waves because it's just like closing, and the light will be emitted in front of that of the shrimp, right?
That's
So
because we need the standing waves to get it to repeatedly cavitate, whereas the pistol shrimp, when it creates it, it's creating a very brief just instance of sonoluminescence,
Mhm.
whereas we're trying to actually have it be sustained.
Repeated.
mhm.
So that's why we need standing waves, whereas they're not needed in nature because of that.
Okay. And I think Jackson got a question.
Yeah. So like in that last slide, you like just mentioned that the luminosity of the light increases with lowered temperature. So why would that happen?
We believe that sonoluminescence, the luminosity or the intensity, is related to the surface tension or viscosity of the fluid, and lowering temperature and raising salinity would increase both of those variables.
Okay.
You may have talked about it and I missed it, but how exactly do you suspend a bubble in water?
Yeah, I can answer that. So that's because of the standing waves in the water. They once the bubble hits a certain point, it will be like in a if it in a spot where if it moves down, it'll get pushed up, and if it moves up, it'll get pushed down
That's what I was thinking.
because of those standing waves. Yeah.
Okay.
I have two technical questions. Okay. One, how does one degas water?
There are two methods. You can either boil it and cap it after it's boiled and then let it cool back down, or you can use a pump to lower the pressure, which will pull the gas that's been trapped in the water. It will lower the partial pressure of that gas, causing
So
it to
it
come
boils it,
out.
so you boil it
Basically,
both ways?
yes. Yes, but one is you boil it with heat,
Yeah, I
and at least you boil it
understand.
with
Which
fat.
one did you do?
We used heat to boil it.
Heat,
Yeah.
okay.
Yeah, we-
And my second question is perhaps better addressed to a German speaker. When did Bremsstrahlung become abbreviated to Brems?
This is actually a point that I made to them, because if you say Bremsstrahlung radiation, then you say Strahlung is just the same as radiation.
Yeah, it means
So-
breaking radiation.
It means breaking radiation, and as a German, I'm perfectly fine to hear Brems radiation, but I'm not fine with hearing Bremsstrahlung radiation.
I've
because
never
that
heard
doesn't-
Bremsstrahlung radiation ever used here. I've only
Ah,
ever heard
okay.
Bremsstrahlung.
Oh, okay.
Okay.
Yeah.
Okay.
Fair question,
Okay.
anyway. But
We didn't get to that in my German
But you say
class.
Eigenvalue, right? You say Eigenvalue. You don't say Eigenwert. Why don't you say Why do you say Eigenvalue?
Because we're English-speaking people.
Okay. Okay, I think we should discuss this in more detail, but maybe not
If you
right
want to
now.
have an irrational discussion, we should go to a bar.
Sounds good to me. Yeah. All right, more questions.
I have a
please.
question.
Yeah.
So did you actually constructed LC oscillator with a glass attached to your what, transducer?
We don't have all the materials
Yeah.
yet.
Yeah, we're
Yeah.
waiting on materials
Yeah.
at the moment.
Oh, okay.
Yeah.
So I wanted to ask what happens if you attach flask to the transducer what happens to the resonance frequency of AC circuit. But since you haven't done it, maybe I'll ask.
I think I will definitely change it. Yeah.
Okay.
I would
ask
think.
during final presentation.
I'm a little bit surprised about the wavelength and the size of the flask. I would expect the wavelength to be shorter, actually. Yeah, maybe we go through the math once more, but it's just surprising to me. But okay, I don't really know. Jackson, you got another question?
Yeah. So you mentioned that the water needs to be degassed. So how do you prevent the gas from the bubble itself from dissolving into the water?
I assume surface tension.
That's what the standing wave does. Is it also helps to keep it as a cavity because it's running at a resonant frequency. So it's like helping create the cavity inside it, if I remember
Oh
correctly.
yeah, that's true. Yeah, the bubble cavitates, so it's kind of being forced open. Yeah.
Maybe you should also, or did you explain how the bubble actually comes into the water so that you take a pipette or
Yeah,
something
yeah,
like that?
yeah,
That's
that's
it.
right. And we draw.
Mhm. That's maybe an important piece of information. Mhm.
I think
More
we mentioned
questions?
that. I think so. Yeah.
Okay, then thank you very much.